In the previous video, we discussed the theory behind the energy levels in organic materials and the reason behind the conductive nature of some organic molecules. In this video, we will look at the concepts that are important to understand the electronic behavior of organic photovoltaic solar cells. We will begin with the concept of an exciton and understand the difference between an exciton and a charge carrier. You will then learn how and why doping is achieved in organic materials. The formation of heterojunctions and the charge separation in these simple heterojunctions will then be discussed, and finally we will conclude by looking into the concept of bulk heterojunctions. We are familiar with the charge carriers in semiconductors, which are negatively charged electrons and positively charged holes. Upon being excited by an incident photon, an atom in the lattice absorbs the photon energy and utilizes it to excite an electron from its valence band to the conduction band. The excited electron leaves behind the positively charged hole in the lattice. Due to the difference in charge, there is an inherent Coulomb force of attraction between the electron and hole, which is called the binding energy. In most inorganic semiconductors, the force of attraction between these two charges is very minimum, and they can easily be split into independent charge carriers. In organic materials, however, the properties of the material cause an increased Coulomb force of attraction between the excited electron and hole. This high binding energy prevents the complete separation of electrons and holes upon being excited with high energy photons. As a result, complete charge separation does not take place, but an exciton containing both electron and hole is formed instead. This exciton can be imagined as a sphere that moves around containing an electron and the hole bound by a mutual Coulombic forces of attraction. Splitting of the electron and hole does not take place unless the exciton is subjected to a strong electric field. An important limitation posed by this exciton is high recombination rate. Due to the stronger binding forces between the hole and the electron, the likelihood of electron-hole recombination is very high. This gives rise to very low diffusion lengths. Under normal condition, the diffusion length of these excitons is 1 to 20 nanometers. Of course, this affects the design of organic photovoltaic cells. The exciton binding energy can be quantified by the electrostatic potential energy that follows from the Coulomb's law of attraction. In this equation, we see both charges Q1 and Q2 in the numerator and the distance r between the charges in the denominator. Both the electron and hole are equally charged but opposite to each other. The equation also includes the relative permittivity of the material. Organic materials often have a low relative permittivity such that the binding energy of the exciton is high. It is common practice to calculate a certain distance at which the thermal energy at room temperature can split the exciton, which is the case when the exciton binding energy equals kT. This so-called critical distance is then found by this equation. As you know, effective charge carrier separation requires an electric field. In conventional semiconductors, the internal electric field is generated by a p-n junction. The p-n junction is created by introducing dopant atoms in the semiconductor materials with either fewer or additional valence electrons. However, doping also increases the number of defect states, which leads to increased Shockley-Reed-Hole recombination. Doping, therefore, effectively decreases the diffusion length of the semiconductor material. With an already low diffusion length due to excitons in organic absorbent materials, doping is generally not the preferred method to obtain a p-n junction. We tackle this issue by the use of intrinsic materials. At this point, let us recall some definitions that will help us understand the concept of doping and charge separation in organic solar cells. As you already know, the energy band diagram is a visual representation of the energy levels of the conduction and valence bands along with the band gap of a material. In addition to this, it also shows us the vacuum state. Electrons in a material are naturally bound with the surface of the material and cannot freely diffuse into the free space around it. This is due to a certain energy barrier that prevents the diffusion of electrons into free space. The vacuum level can be visualized as this energy barrier, making it the minimum energy possessed by an electron present outside the material. It can thus be defined as the energy of a free stationary electron that is outside any material. Ionization potential is defined as the energy required to excite an electron from the valence band, or HOMO, to the vacuum energy level. In the energy band diagram, this translates to the difference in the energy between the vacuum state and the valence band, or HOMO. Using this definition, we can infer that a material with a low ionization potential requires very little energy to excite an electron from its valence band to the vacuum state. This allows us to refer to such material as electron donors. Electron affinity is defined as the energy released while moving an electron from just outside the semiconductor to the bottom of the conduction band. This can be represented on the energy band diagram as the difference in the energy between the vacuum state and the conduction band, or the LUMO. A material with a high electron affinity can therefore easily attract an electron into its conduction band from the vacuum state and is therefore called an electron acceptor. So far we have discussed the principle of an exciton and how materials can be classified as electron donor or electron acceptor material based on the ionization potential and the electron affinity. In the next video we will continue our discussion of organic photovoltaic solar cells by bringing these materials together to form a heterojunction.